Okay, let's get back into it. So, let me just remind you that a partial order, which is kind of what all these terms refer to, a partial order is a relation on a set A, which is reflexive, transitive, and antisymmetric. So less than or equal to is a partial order on A means less than or equal to is reflexive, meaning A is less than or equal to A for all A. Less than or equal to is antisymmetric, which means A is less than or equal to B, B is less than or equal to A, implies A equals B. And less than or equal to is transitive, which means that A is less than or equal to B and B is less than or equal to C. That implies A is less than or equal to C. Okay, so that's what a partial order is. Okay. And okay. So let's talk about what a chain is. We have a definition. Okay. Again, A is a partially ordered set. We'll just say with a partial order less than or equal to a chain. A is a subset B such that for all AB in our subset, A is comparable to B. Okay. We had a name for a set with a partial order such that any two elements are comparable. We called that a total order or a linear order. So what we could say is that so B is linearly ordered by less than or equal to. And well, I'd like to think of this with a picture. Here's my picture. Okay. Oops. Okay, so maybe in this picture, like the lower down dots are less than or equal to the ones that are joined to them higher up. And this relation is supposed to be transitive. So this thing is like less than or equal to this thing, which is less than or equal to this thing, for example. And so this is just like some wacky linear, some wacky partial order, but a chain is something that kind of like any two things are comparable. So a chain might look like this. Okay, and then in this line of squiggles, any two things are comparable. Whereas in the, you know, you can kind of maybe guess that in the entire thing, like this thing and this thing are not comparable. There's no line between them. You know, well, all these arrows, the arrows only go up. So I'll just put arrows so that they only go up. I think that's all the arrows. Right. So this is a chain. Okay. So it's a subset in which any two things are comparable. Okay. In the entire partially ordered set, there might be lots of things that aren't comparable to other things, but in this subset, everything is comparable to everything else. Okay, so that's a chain. So let's start talking about least elements. Okay. The name of least element kind of tells you what the definition should be, but let's write it down anyways. Again, A is a set with partial order less than or equal to an element little a is the least element of less if it's less than or equal to everything else. Okay. And in our example, there was no least element because there's nothing lying below all these bottom ones. Okay. So a least element is comparable to everything else and less than or equal to everything else. Okay, so that is pretty special. It is similarly, you can kind of try to guess what minimal might mean. And it is just slightly different than least. Okay. A minimal element. So a least element is less than or equal to everything else, but a minimal element is not bigger than anything else. Okay. So now the trick is we just have to rewrite the phrase not bigger than anything else in a rigorous fashion. So again, A is a partially ordered set. An element A is minimal if for all B, if B is less than or equal to A, then B equals A. Okay. So minimal means there's nothing below it, least means it's below everything else. So these two things are different. Just to give a concrete example, A might be the set 1. I don't want to say 1, 2, 3. Maybe the set A, B, C. And where we have A is less than or equal to C, B is less than or equal to C. And of course, A is less than or equal to A, B is less than or equal to B, C is less than or equal to C. Okay. So then A and B are both minimal. But there is no least element. Okay. On the other hand, the same example A, but if I use a different, or let's say B equals A, B, C, D, and A is less than or equal to B, oh, sorry, A is less than or equal to C, B is less than or equal to C, and D is less than or equal to A, D is less than or equal to B. And then there you get like, as long as you assume that the less than or equal to is transitive, you get lots of other relations, like you get D is also less than or equal to C, D is also less than, yeah, and stuff like that. Okay, now D is actually the least element. D is less than or equal to everything. Okay. Okay. And notice that D, being a least element, is also a minimal element. Okay, and then we have a theorem. Trying to read theorem that A be a set with partial order less than or equal to let B be a subset of A. So B has at most one least element 2. If B has a least element, that element is also minimal. Three. Okay. If B is a chain, meaning that it's totally ordered, or any two elements are comparable, then a minimal element, or I should say then every minimal element is also a least element. Oh, and again, I wasn't sticking to my borders. Sorry about that. Okay. So Let's just show the third property of that if every element of B is comparable, all the elements of B are comparable, then let's show that a minimal element is also a least element. Let's do proof of 3. Okay. Assume B is a chain. Let A and assume that it's a minimal element. So that means for all B and B, if B is less than or equal to A, then B equals A. Okay. Now we have to show that A is less than or equal to all the elements of B. So let's see. C be an element of B. Oh, and I should have said let A be an element of B as well. Sorry. So C is an element of B. Now B is a chain, so A and C are comparable. Since B is a chain, and comparable means that either A is less than or equal to C or C is less than or equal to A. Okay, you can say either A is less than or equal to C or C is less than or equal to A. Okay, and now we can kind of see what happens. We want A to be less than or equal to C. So if A is less than or equal to C, we're done. If C is less than or equal to A, well, A is a minimal element, so C equals A. And then also, since C equals A is less than or equal to C, because A equals. Just write that down and then we'll be done. The third part. Okay, so we need to write that down. We need to write first case is that A is less than or equal to C. Well, that's exactly what we want. Because we need to show that A is less than or equal to all the elements of B and C was some arbitrary element of B. Okay. So the other case is that C is less than or equal to A. Okay, we're not quite done yet, but A is minimal. So C equals A since A is minimal. Okay, but A is less than or equal to A, so A is less than or equal to C, because C and A are the same thing. And A is less than or equal to A, since less than or equal to is reflexive. Okay, and we are done in this case. So in both cases, A is less than or equal to C, so A is less than or equal to everything. So A is less than or equal to C for all elements of B. So A is the least element. That's the end of this proof. Okay. And I guess that is it for class today. So remember, assignment 2 would be due Friday. And if you get stuck on a question or something, please email me. I'll try my best to respond like pretty fast. okay, to give you a chance, to give you a good chance to finish before Friday at 5. Okay, or if you don't need help, well, that's great too. Okay, but I guess that's it for me today. Thank you everyone for watching. Oh yes, that is a good point. I did just post it, but I just posted it right before class, but it has to decode it or something. It should be ready to watch soon. Yeah, but thank you for reminding me because I was very late to post it. Okay. Okay, bye everyone.